Unit 4 focuses on all things probability, with Chapter 14 starting with basic probability problems. Now, this unit is unique for a few different reasons. First and foremost, we're doing actual math in this problem. We're multiplying events, we're adding them, we have fractions. So it's a bit different than the last unit in particular, where we have very wordy answers. It's still a stats class, there's still words, but there's a lot more math than we've been used to in the previous chapters. Also, it's different in the sense that these are the types of problems that you were expecting to see in a stat class. You probably weren't expecting to see normal curves or linear regressions or simulations, but we're expecting to see more on the lines of flipping a coin, drawing cards from a deck, and those types of problems. We'll be seeing those in Chapter 14 and Unit 4 in general. As always, let's start off by getting the vocabulary out of the way. A random phenomena is when we have a situation where we know what outcomes could happen, but we don't know what particular outcome did happen or will happen. Take, for example, rolling a die. We know that we're going to get a 1 through 6 every time we roll a die, but we don't know which of those outcomes is going to result. There's also a few different terms that we should be familiar with, such as trial, outcome, and event. We saw those all with simulations, and they largely mean the same things. Event is the accumulation of certain outcomes. Outcomes are the result of an individual trial, etc. Unique to probabilities are what's called a sample space. A sample space is the collection of all possible outcomes. When we're completing a problem where all the possible outcomes are equally likely, that's referred to as a theoretical probability. Think rolling a die, flipping a coin, or spinning the extra credit wheel in Mr. Sager's classroom. The equation for theoretical probabilities on the bottom here. So if, for example, we were asked to find the probability of rolling an even number on a standard die, we would take the number of outcomes that are even, which is 3, and divide it by the total number of possible outcomes, which is 6. 3 over 6 gives us a probability of 50%. Now, in most cases, probabilities are not equally likely. Let's take, for example, a person shooting free throws, basketball free throws. In pretty much every scenario, this person is not shooting, making and missing these free throws with equal probability. Okay? A skilled basketball player is making these free throws with a higher than 50-50 chance, and a poor basketball player is probably making less than 50% of the free throws. So events are not always equally likely, and we want to make sure not to assume that if it's not the case. There's another important concept referred to as the law of large numbers, and there's a definition up on the screen which I'll allow you to read on your own. But to summarize it, let's say we are flipping a coin, and we're recording the proportion of heads that we get when we flip this coin. Now, we know that a coin results in 50% heads, 50% tails, but that's over the long run, and that's really what the law of large numbers is saying. If we flip this coin 100 times, we might not see 50% of each. We might see 55% tails. Heads, or we might only see 45% heads. That wouldn't be unusual. The more trials we take of flipping this coin, we should expect that to coincide closer and closer to the actual probability or the empirical probability of the proportion of heads we would get, which in this case is 50%. So this is talking about the long run, the infinitely long run, and the only time that we're actually going to see 50% heads, 50% tails from a coin is if we flipped it an infinite amount of times. There's also something called the law of averages, and this is actually something that doesn't exist. Let's say we were to flip a coin and 10 times in a row it comes up heads. Law of averages is the tendency for people to believe that since we had a string of heads, that now tails is due to come up. The coin doesn't have any memory. It doesn't know that it just flipped 10 for the last, or heads for the last 10 flips. We're still a 50-50 chance for both heads and tails. When we're asked to give a subjective or a personal probability to a problem, we don't have any data or mathematical justification for our answer. We're just using our personal experiences to kind of ballpark an estimate. On your notes, I believe it's example 2, references a problem where It asks you to estimate the probability of being stuck in the next elevator you ride. This is entirely a personal probability question where you're looking at the number of elevators you've ridden in your life or estimating it, asking yourself how many times have I gotten stuck on an elevator, and using those two numbers to come up with a ballpark probability to answer the question. Just like Unit 1, it's always helpful to make a picture when we're dealing with these types of problems, and the most common picture when it comes to probabilities is a Venn diagram. Here are a few key rules having to do with Venn diagrams and probability. So the first is that a probability is always a number between 0 and 1. 0 is the probability corresponding to an event that is impossible, and 1 is the probability of an event that's certain to occur. Next, thinking back a few slides, the sample space is the complete set of all outcomes of an event. That's represented by this box here. The probability, if we look at the entire sample space, must total 100%. There's also something called the complement rule. Now, the complement is kind of like the opposite of an event. Let's say we have an event called event A, and that's represented by this greenish-blue circle here. Okay, so the probability of A is the area inside that circle. The square is the full sample space. Everything in the square totals 100%. The complement of A is everything in the sample space that's not included in that circle. So together, the circle and its complement, A and the complement of A, make up the full sample space. So if we wanted to find event A, the probability of event A, we could take 1 minus its complement, or vice versa. If we wanted to find the complement of A, we could take 1 minus the probability of A. Now let's move on to probabilities involving two events, and let's start by defining the term disjoint. Disjoint means that two events cannot happen at the same time. We can see in this Venn diagram that event A has no overlap with event B. These two events are disjoint, or also known as mutually exclusive. They have no common outcomes, so there's no way that one event can be in both event A and event B. Now, when we do the addition rule, we first want to associate it with the word or. So to find the probability of A or B, we just take the probability of A, add the probability of B, and it's as simple as that, as long as those two events are disjoint. The multiplication rule is similar. We're just going to take the probability of A, multiply the probability of B. A couple things to note. So first off, previously on the addition rule, it used the word or. So for the addition rule, the probability of A or B meant either of those two things could occur or they both could occur. With the multiplication rule, it uses the word and. So probability of A and B means that both of these events have to occur. Also note that on both these slides, it's referencing independent events. At this point, hopefully we're becoming more familiar with that word. It means that when event A occurs, it's not influencing event B. In other words, the probability of B is not changing based on whether or not event A occurs. Here's a Venn diagram for the multiplication rule, and we can see that events A and events B are not disjoint, and they overlap in this center section right here. Now, this center section is actually the solution to the probability of A and B occurring. So the overlap is where they both occur at the same time. This is also the reason that they're not disjoint or mutually exclusive. We've come to the main example problem, so as usual, pause the video, read the problem, attempt them on your own, and hit resume when you're ready to go over them. Now, it's not unusual for them to throw a few different numbers at you in a problem like this. It notes that back in the 1990s, these polling organizations could only reach 69% of the households. This is actually a decoy number that we're not going to use. The one that we're interested in is this one down here, the 76%, and it's the more recent one that they found in 2003. Now, another thing that we should note is that if they have a 76% chance of contacting a household, that means that 1 minus that, or 24%, is the chance they have of not contacting or not making contact with a household. For simplicity, for the rest of the problem, I'm going to let the variable C represent a household that they made contact with, and N represent a household that they didn't make contact with. So the answer to A is just 76%. Now B, what's the probability that an interviewer successfully contacts both of the next two households on her list? In other words, they need to make contact with the first household and the second household, where and means multiplication. We get 0.5776, and we normally round our probabilities to 3 decimal places, 0.578. Part C, what's the probability that the interview's first successful contact will be the third household on the list? For this to happen, it means that the first two households they called, they didn't make contact with. In other words, they have 2 that were no contact, followed by a third that they made contact with. 0.24 times 0.24 times 0.76 gives us this number right here. We're rounding to 3 significant decimal places, which means we don't count that 0, and we start counting the 3 significant decimal places with that 4 there. Okay, we're going to round that 7 based on the number after it, 0.0438. Part D, what's the probability that the interviewer will make at least one successful contact among the next 5 households on the list? Now, this one's a bit tricky. Now, let's start off by thinking about all the different ways we can contact 5 households, contact or not contact 5 households. So we could end up contacting all 5, ranging from not contacting all 5, and there's a whole bunch of scenarios in between those two that are a mix of contacts and non-contacts. Now we want to find the probability of making at least one successful contact in the next 5 households. So if we were to make this whole list, which by the way, this is not the correct way to write out the sample space, but it should give you an accurate idea of what we're doing here. If we look at this whole list here, the only one that doesn't have at least one successful contact is going to be this one way at the bottom. So all these ones in the middle here, including all these dots that aren't written, are going to have at least one C in there. The only one that doesn't is where we call all 5 of these households, and none of them pick up the phone. We don't make contact with any of them. The key in this problem that tells us it's this type of problem is where we see at least one. Okay, and we're going to solve this with the complement. Rather than find the probabilities of all these and add them up, we're going to find the probability of this one situation and subtract it from 100% to find the total of all these other ones. So here it is on the bottom here. The probability of at least one success is the same as 1 minus the probability of getting no successes in 5. No successes in 5 is 0.24 to the 5th power, and we're going to calculate that and subtract it from 100%. 1 minus 0.000796 gives us our answer, 0.9992. As for what could go wrong, we always want to be aware of probabilities that don't add up to 1. So when you take a look at a problem, just make sure that the probabilities total 100%. Also, don't add probabilities of events if they're not disjoint. We'll learn to do that in the next chapter. Don't multiply probabilities of multiple events if those events are not independent. This is another thing that we'll learn in the next chapter, but for now, we can only multiply independent events. Lastly, don't confuse disjoint and independent. These are 2 different things. In fact, disjoint events can't be independent. That's one last thing that we'll be learning in chapter 15.